Functions and Algorithmic Applications by Josh Alman, Timothy Chen, and Ryan Williams. And Josh will be the
Hi, yeah, thanks for coming. So let me give you a quick outline of the talk before I get started. So I'm going to spend a lot of time giving you the context for our work and the kinds of results we get. So I'm going to talk about polynomial representations, and then specifically how to go from polynomials to some cool new algorithmic results. And I'll focus a bit on some nearest neighbor problems. And then after that, I'll tell you our results, and I'll give you some details and conclude. Okay, so the kind of thing we care about in this work is polynomials which represent Boolean functions. So if f is a Boolean function, it takes n bits to 1 bit, and let's say d is like the fq or the reals or something, then we say that a polynomial p, which also takes n variables, is an exact polynomial for the function f if on any input x, the polynomial evaluated at that x is equal to the function evaluated at that x. So let me give a simple example for the OR function. So the OR function is 0 when all the bits are 0, and it's 1 otherwise. And we can write it as a polynomial like this. So 1 minus the product of 1 minus x of i's. So when all the x of i's are 0, this is 1 minus 1, which is 0. And when any of them is 1, the product is 0, and this is 1. So this polynomial equals the OR function. You can check when you expand this out. This has degree n, and it has 2 to the n monomials. And what we're really going to look for is small polynomials. So polynomials which have smaller degree, or really smaller number of monomials. And you can see that when you're working with polynomials for Boolean functions, really, like you never have to work with degrees bigger than 1, because like x squared equals x when x is 0 or 1. So you only have to look at multilinear polynomials, and really degree n and 2 to the n monomials is the worst you can possibly get. And you might hope maybe we can decrease this by being more clever, but you can show pretty easily that there's a unique exact polynomial for any Boolean function. So we're going to need different ways to represent Boolean functions in order to get smaller polynomials to represent them. Okay, so let me tell you about 3 different ways to represent Boolean functions other than the exact way I just told you about. So the first is one I really like called probabilistic polynomials. So the intuition here maybe is that just like you can try to speed up a deterministic algorithm by making a probabilistic algorithm, similarly you can make a smaller polynomial by using a probabilistic polynomial. So the idea now is instead of having a single polynomial, we're going to have a distribution, capital P, on polynomials. And this distribution is going to have some error parameter epsilon, and then we're going to say that this distribution is a probabilistic polynomial for the function with error epsilon if for any input x, the probability over drawing a polynomial from the distribution that the polynomial correctly evaluates the function on that input is at least 1 minus epsilon. So it's really important that this is a worst case error over all inputs. So for each input, it has this chance of being correct. And this is going to be important for making worst case runtime analysis later on. So let's look at the OR function again, say over f2. So the idea is we need to construct a distribution on polynomials. So what I'm going to do is I'm going to give you a randomized algorithm that at the end outputs a polynomial. And then the induced distribution on polynomials from this algorithm is our probabilistic polynomial distribution. So the random input is just going to be a random subset from 1 through n. And then what we're going to do is we're just going to sum the x of i's for the i's that we picked in our random subset. Okay, so why does this work? Well, it's definitely 0 when all the inputs are 0. And you can check that when some of them are 1, this is odd with probability 1/2, just like whether or not you pick the last one to be in the sum or not. Okay, this doesn't seem great, right? Error probability 1/2 we could have gotten with just a constant polynomial. But you can amplify the error epsilon with degree about log 1 over epsilon by just taking log 1 over epsilon independent copies of it and then the exact OR of all these things. And we're really taking advantage of the fact that when it's 0, it's always correct and gives a 0. Okay, so this is pretty good. This is much better than degree n. But let's look at another case where we can get even better. So a polynomial threshold function, or PTF, now we're only going to be able to work over the reals, not finite fields anymore. This is a single polynomial now, where instead of outputting 0 or 1, depending on whether the function outputs 0 or 1, We just are going to guarantee that it gives a non-negative number when the function outputs 1 and a negative number when it outputs 0. So you can figure out the value of the function from the sign of this polynomial. And for the OR function, it's super easy to make one of these. You just take a sum of the input bits and then say subtract a half at the end. So if they're all 0, then this is minus a half. And if at least one of them is 1, this is at least a half. So this is great. This is like as low degree as we could hope for, degree 1. Really few monomials. It's really good. But in other cases, we're not going to be able to design such low degree PTFs. And we're going to use one last notion, which is like a really natural combination of the last two I told you about, called probabilistic PTFs. Where here, we're going to have a distribution on polynomials, where the guarantee is that for each input, there's a high chance that it gives a correct PTF value on that input, so positive or negative when it should be. And we're going to be able to design really low degree probabilistic PTFs later. Okay, so why do we want these polynomials? I guess classically, I'm gonna show you this great animation about turning polynomials into algorithms. So I guess usually what polynomials for Boolean functions are used for is you would take some kind of circuit of low complexity and you'd want to prove a lower bound against it. So you would convert it in one of these ways into a nice polynomial, which is nice that it has low degree or low number of monomials or something. And then by proving that some other function doesn't have such polynomials, you prove a lower bound against the class of circuits. But instead we're going to do something different, which has arisen in a bunch of really cool recent results, where what we're going to do instead is we're going to find some kind of classical algorithm, like all sorts of algorithms you're used to, and I'll give you examples in a second, where one of the steps in the algorithm can be interpreted as the problem of evaluating a low degree circuit on lots of inputs. And then if you take that circuit evaluation problem and convert it into a polynomial, and then use fancy algebraic techniques like fast matrix multiplication or fast Fourier transforms, you can get faster algorithms for these like classical problems. And this has been used for a whole bunch of different areas really successfully. And later I'm going to tell you a bit about these nearest neighbor problems. Okay, so let me first elaborate a little bit on this multi-point evaluation and show you one way to go about doing this, which will be useful for our applications later. So what we're going to do is reduce from polynomial evaluation to some matrix multiplication problem. So let's say we have a polynomial which has like some x variables and some y variables going into it. And maybe for the Hamming nearest neighbor case, you can think of this as a polynomial that's like determining whether the x vector is close to the y vector in Hamming distance, as maybe a running example. And what we want to do is we have two big sets A and B, and for each x and A and each y and b, we want to evaluate this polynomial. Well, this really nice trick is that we're going to expand out the polynomial in terms of the monomials. So maybe it looks something like this. And then notice that this can also be written as an inner product by just taking an inner product of the vector of the coefficients in the x part of each monomial and the vector of the y parts of each monomial in this really simple way. Okay, so now when we want to evaluate the polynomial on all pairs of an x and a and y and b, we like construct this x vector for each thing in A and this y vector for each thing in B, and we just need to multiply these matrices together. So if you use fast matrix multiplication, you can get a result that looks like this, that if A and B have size n, and the polynomial is not too big, so say the polynomial has at most n to the 0.1 monomials, so that we can use rectangular matrix multiplication, then we can evaluate it at all points in, you should read this as just about n squared time. So this saves on, like the naive thing to do would be for each pair of an A and B, you like run in n to the 0.1 time over all the monomials and evaluate it, and that would take n to the 2.1 time. So we're really saving that 0.1 in the exponent of n by using this method instead. Okay, so how are we going to use this to solve some nice problem? Well, the problem I want to tell you about is the Hamming nearest neighbors problem. Really the all points Hamming nearest neighbor problem. So here we're given our two sets of n points that are 0, 1 vectors of length d. And let's say d is c log n, where c can be growing with n, but it's probably easier to just think of c as a constant here. And what we want to do is for each x vector in A, we want to find the y vector in B that's closest in Hamming distance to x. Okay, So there's some like pretty simple algorithms you can get for this problem, like n times 2 to the d time or n squared times d time. But we really want something more clever and something like a subquadratic in n time algorithm for this problem. All right, so here's our evaluation lemma that we're going to do again. And sort of the really most straightforward thing to do is just let this a be that a and this b be that b. And what do we want our polynomial to do? Well, maybe we're going to have our polynomial just actually compute the Hamming distance like I told you about before. And so maybe for a given threshold value k, we're going to figure out whether the number of entries that two vectors are the same in is at least k. And then by evaluating this on all pairs of vectors, we can find where the close vectors are. And this is really easy to do. Like here's a PTF for this, for instance. You just sum up over each index this like very simple degree 2 polynomial for determining whether the entries are equal or not. And then you compare it to, say, k minus a half to see whether they're the same in at least k entries. Okay, so this is great. But the problem is when you plug it into our evaluation lemma, we're still going to get an n squared time algorithm, right? This, the runtime here is n squared. So if a and b actually have size n, we're definitely going to get an n squared time algorithm. And we want something subquadratic in n. So we're going to use, here's the evaluation lemma again. We're going to use a modification of this where we're going to plug fewer things in for a and b. So we're actually going to group a and b into, say, n over s groups of size s. So now our polynomial, instead of taking in 2 vectors, is going to take in 2 groups of vectors. And what we want is that the polynomial is going to determine whether there's a close vector among these 2 groups rather than just among 2 vectors. So to write this out as a circuit, if we let, say, at least k is this function which outputs 1 if the sum of its inputs is at least k, so like a threshold function, then we want to look at this circuit here where, well, this at least k of equalities is sort of the same thing I was talking about before. So each equality gate is testing whether 2 bits are equal or not. So they're sort of computing each component of the Hamming distance. And then the at least k gate is determining whether these 2 vectors are close or not to each other. So before, we sort of designed a polynomial for the at least k of equalities. But what we actually want to do is compute a polynomial for the OR of s squared copies of this, where each copy is doing one different pair from the 2 sets of size s. So this circuit, like we said, outputs 1 if there's some pair of points with Hamming distance at most d minus k. And actually constructing a polynomial for this circuit with few monomials will just give a faster algorithm for the problem at the top in basically the same way I said before. It's actually solving a slightly different problem of detecting close pairs, like whether there's a pair of distance k rather than like finding for each red one a close blue one. But there's a simple reduction between these 2 problems. Okay, and actually in previous work that I did with Ryan, we solved this problem in this way. And we got an algorithm like this that when the dimension is c log n, gets randomized time n to the 2 minus this 1 over c log squared c term. And how you should think of this is when c is a constant, then this is really n to the power of some constant minus 2. So it's a truly subquadratic time algorithm in that case. But we're actually going to improve on this algorithm here. So yeah, and the way they got this, the way we got this was with a nice probabilistic polynomial for this OR of thresholds function, actually. Okay, so let me tell you about our new results. And these are going to be 3 different polynomials for computing an OR of these at least k threshold functions. And actually, in addition to these like Hamming nearest neighbor problems, there's tons of problems which can reduce to evaluating these kinds of circuits that I'll tell you about in a second. Okay, so the first is that we're going to design a probabilistic polynomial that uses less randomness. So we're going to get degree root d times log s when the error is 1 over s. And it's only going to use polylog in DNS number of random bits. So the best construction for a probabilistic polynomial before had the same degree, but used a linear number of random bits. So we're going to reduce that a lot. And you might ask, well, can we reduce the degree? But actually, Razborov and Smolensky showed in the 80s that this is a tight degree lower bound for the threshold, or every symmetric. Well, the majority function requires this degree. And so we can't hope to improve this for every symmetric function. Okay, and this is going to help to make, like, intuitively, it'll help de-randomize algorithms, I guess, by using less randomness. So the second thing we're going to do is we're going to construct a nice PTF for the threshold function. So making a PTF for the threshold function is super easy. You just add the bits and subtract k, or what we did before. But what we want is actually that we're going to output, when we want to output a negative number, we're going to output a small negative number. And when we want to output a positive number, we're going to output a big positive number. And that way, by adding s copies of this together, we can actually compute the OR of s copies of the threshold function like we want. And we're going to get the same degree as for probabilistic polynomials here. And then finally, for probabilistic PTFs, where we're still going to have this nice notion of small if it's negative and big if it's large, big if it's positive, we're going to be able to get an even lower degree of d to the 1/3. And this is really where a lot of our new results are going to come from, being able to get a lower than square root of d degree. Okay, so let me tell you the main applications, and there are actually a lot more that you can find in our paper later if you want. So the first is to these all points nearest neighbor problems. So given n red and n blue points, and you can think of d as like 0, 1, or the reals even, with dimension c log n, we can find the Hamming nearest neighbor, nearest blue point for each red point in this randomized time n to the 2 minus 1 over about root c, or deterministic time n to the 2 minus about c. So this runtime was the randomized time we got in our old paper, but we de-randomize it by getting a deterministic runtime with a deterministic algorithm with the same runtime. But if you're willing to have a randomized algorithm, we can also speed it up. But then we also look at the approximate nearest neighbor problem, where for each point you want to find an approximate nearest neighbor. And there, we can get an n to the 2 minus epsilon to the 1/3 time algorithm. So if you think of epsilon as a constant that you want to approximate by, this is a truly subquadratic time algorithm that's almost independent of what the dimension of the vectors is. And this improves on, like LSH gets about an epsilon there, and there's an algorithm by Greg Valiant that gets like a square root of epsilon there. So we improve it to epsilon to the 1/3. And then we also get some results in circuit complexity theory. So we I guess, use this technique to get some new faster circuit SAT algorithms for some classes of circuits. So the first is these circuits with some ACC gates at the top, and then 2 layers of threshold gates with some conditions on exactly how big these things are, where we can get a faster than brute force running time SAT algorithm for this class of circuits. And because it's a deterministic algorithm, it also implies lower bounds against this class of circuits. So this is, I guess, the most complicated class of circuits that has threshold functions in it that we can prove a lower bound against. And then also, we can give a randomized non-trivial SAT algorithm for these kinds of circuits that have 3 layers of threshold gates in them. So unfortunately, it's randomized, so it doesn't give a lower bound, but it would be really cool to de-randomize this. So let me tell you a little bit about how we construct some of our polynomials. I guess I don't want to talk too much about the probabilistic polynomial, because the idea is really to sort of take the construction from our old paper and then be a little bit more clever in the analysis at the end, and notice that you only need limited independence. So what I really want to focus on is how we get our nice PTFs. So remember, what we want is a PTF such that when it's not at least k, we output a small negative number, and when it is at least k, we output a big positive number. And the big idea behind how we're going to do this is to use Chebyshev polynomials. So anyone who went to the orthogonal polynomials workshop the other day knows there's these nice Chebyshev polynomials. They have lots of equivalent, really nice definitions. But what we really care about is that they have really nice threshold behavior. So between -1 and 1, they're bounded in this squiggly shape between -1 and 1. But then right when you pass 1, they start blowing up as quickly as possible. And in fact, among all like fixed degree polynomials, the Chebyshev polynomial is the one that, given that it's bounded between -1 and 1 here, it blows up the fastest for every point beyond 1. And if you just sort of take the sum of the inputs and do an affine transformation to put everything where you want, you can get this to give a degree root d times log s polynomial. But like I said, we can actually get square root log s instead of log s. And the way you do this is to notice, well, the Chebyshev polynomial is guaranteed to be bounded between 1 and -1 in this entire interval here. But actually, we're just going to be mapping like k in evenly spaced points into this interval, and we only need it to be between -1 and 1 at these k points. It's actually okay if it gets bigger at the points we're never going to evaluate it at. And there's actually another construction due to Chebyshev. This is 1899, not 1999. Called discrete Chebyshev polynomials that have some definition that's a little bit messier, but about the same. And they look like this, where like at each up to, this is the one for k equals 12, I think. So at each like integer between 0 and 12, it has like a root or almost a root. But between, it's fine if it like gets way bigger than it really needs to be. And if you use this instead, so with less constraints, you get the degree I told you about here. Okay, and then the idea between the nice probabilistic PTF is really to combine the two ideas. It's a bit messy, so I don't want to talk too much about it. Okay, so yeah, just to conclude, I guess it'd be really interesting to see what's the power or limit of these probabilistic PTFs and see if they could be used to speed up some other algorithms. It would also be cool to de-randomize this SAT algorithm with 3 layers of threshold gates because it would prove new, more powerful lower bounds. And I guess this approximate nearest neighbor problem is pretty interesting to lots of people. So it'd be interesting to speed it up more or prove that you can't. Thanks. Yeah, I mean, so like the way we use matrix multiplication is just to evaluate a bunch of polynomials. So like it seems more natural, I think, to use something else like FFT to evaluate the polynomials instead. But this is the only way I've been able to come up with at least that gets like exactly the right dependencies between the different parameters we need. So I think it's possible, but I don't know how. Yeah. Yeah, that's right.